Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Optimization of high-speed cutting parameters oriented improves the dimensional accuracy of alloy steel SKD11 Duong Van Dao11 Dong Nai Technical College, Vietnam on Tuan Lai2, Tien Lap Do2, Van Tuan Pham2, Cong Doan Le2, 10 LOC NGO22 Advanced Technology Center, Le Quy Don Technical University, Hanoi, Vietnam Abstract. This paper focuses on evaluating the influence of cutting parameters on dimensional accuracy when high-speed finishing milling, HSFM, of alloy steel SKD11 after heat treatment, 55 HRC. At the same time, the problem of finding the optimal cutting parameter that ensures the smallest dimension error is solved through the genetic algorithm, GA. The optimization problem has constraints both on the value limit of the variables and the limit of the objective function. The experiments were carried out based on the orthogonal experimental method of level 2 with the construction of a system of regression equations describing the relationship between cutting parameters and dimensional accuracy. The research results show the reliability of the regression equation and contribute to improving the machining quality when HSFM of alloy steel SKD11 after heat treatment. Keywords: high-speed milling, alloy steel, dimensional accuracy, optimization. Introduction. High-speed machining, HSM, is a metal cutting method with a cutting speed of 5 to 10 times that of conventional machining. The temperature at the cutting area will be reduced because it is transferred to the chip 1. The HSM method has many outstanding advantages when gradually increasing the cutting speed, such as increased cutting productivity, increased surface quality, and reduced cutting force. However, as the cutting speed increases, the tool life decreases. Compared with traditional machining, HSM has outstanding advantages. High-speed machining can reduce machining times by up to 50% and reduce machining costs by 30 to 50%, depending on the case too. In metalworking and cutting, processing hard materials in general and hard alloy steel, in particular, is always a difficult problem, complicated by physical phenomena of the cutting process as well as different processing requirements. Distinguished from HSM of aluminum, low and medium hardness alloys, below 30 HRC, or traditional machining. However, in practice, if the basic characteristics of the cutting process are understood and the problems are solved correctly, hard alloy HSM becomes a predictable process. At this time, the problem of processing and cutting hard materials and hard alloy steel will become more favorable and bring high economic profits. It is easy to see that alloys such as titanium alloys, alloy steels after heat treatment, hardness above 40 HRC, are difficult materials to cut due to their high hardness, high thermal strength, chemical abrasion resistance, and high temperature resistance. Temperature and stress are always high in the cutting zone during machining due to poor thermal conductivity, affecting tool wear and chip morphology, increasing machining costs. In other words, when it comes to the HSM of hard alloys, we are often interested in the ability to machine them. Machinability refers to the ease with which a material is cut to the required texture. Factors such as cutting force, cutting heat, vibration, surface quality, tool wear, and wasted energy all affect the finish of the structure, so it can be considered as the basis for evaluating machinability. 3. The problem of HSM of hard alloys has been interested in research in the world for many years. Studies on cutting force can be considered in 4, 5, cutting temperature in 6, 7, vibration in 8, 9, cutting tool wear in 10, 11, roughness in 12, 2, 13. Dimensional accuracy is a key indicator in machining accuracy and is the basis of product quality assessment. This factor is directly related to the ability to assemble in the system and affects the working condition of the whole system. However, few studies mention this issue, only a few case studies such as 14, 15, 16, 17, 18, 19, 20, 21, but these studies are not high-speed machining. The influence of technological parameters on the dimensional accuracy when turning aluminum materials is studied in 14. The results show that when increasing the cutting speed and decreasing the feed rate or vice versa, the dimensional accuracy is guaranteed. The dimensional accuracy is highest when the cutting speed is high, the depth of cut is large and the feed rate is small. The problem of tool wear, surface roughness, and dimensional accuracy when machining AISI 4140 alloy using low-temperature coolant are considered in 15, 18. The results show that the cold coolant helps to reduce tool wear, increase durability, and significantly reduce the dimensional deviation. The method of measuring and analyzing the cutting force and vibration during the steel alloy turning to determine the surface roughness and dimensional deviation based on the neural algorithm is presented in 16. The causes of dimensional deviation including error in machine geometry, cutting heat, control system, and cutting force are described in 17. The study concludes that shear force has the most influence on dimensional deviation. A model which is established in 19 to predict geometric roughness and dimensional accuracy through imaging technology during machining. The parameters obtained by taking pictures are put into the simulation environment, combined with technological IJERT 10 is 060254 www.ijert.org 522. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Parameters, the author can predict the roughness and dimensional accuracy. Experimental verification for some cases confirms the feasibility of the method. The optimal tooling strategy to ensure dimensional accuracy when high-speed milling of very small parts, micromachining, is used in 20. The influence of technological parameters on dimensional accuracy when machining AISI 4340 hardened steel dry turning is studied in 21. The author concludes that cutting speed and CBN coded turning tip radius have the most influence to dimensional accuracy. Due to the limitation of manufacturing technology of machines, cutting tools, and other equipment, there are not many publications on the issue of dimensional accuracy when high-speed processing for alloy steel after heat treatment with high hardness. This paper focuses on studying the dimensional accuracy when high-speed finishing milling of alloy steel SKD11 after heat treatment with hardness above 55 HRC. The relationship between the shear parameters and the dimensional accuracy is shown through the construction of the regression equation. Level 2 orthogonal empirical method is applied to build this mathematical equation. The genetic algorithm with the objective function which is constrained is used to find the optimal set of cutting parameters that minimize the dimension error. Two materials and methods. A experiment set up the experimental objective of HSFM of alloy steel SKD11 after heat treatment, 55 HRC, is to determine the relationship between cutting parameters, depth of cutting, feed rate, and spindle speed, in HSFM with dimensional error through the regression equation. This equation is built based on the level 2 orthogonal empirical method. The workpiece material is SKD11, Japanese standard JISG 4404, with the composition described in TABI Table I. Ingredient SKD11 chemical composition of SKD11 alloy steel workpiece C, %, SI, %, MN, %, CRMO, %, V, P, 1.4 to 1.60.60.6 1113 0.7 1.2 1.10.03 SKD11 workpiece was heat treated in the turbo-Ipson furnace and hardness measured on an FR1E/hard machine, Fig.1. Hardness measurement results with the average value of SKD11 alloy steel workpiece after heat treatment reached 55 HRC. Regarding machining machines, Experiments were carried out on HSM machines DMC1450V manufactured in 2018. The maximum tool speed according to X, Y, Z reaches 42.000 mm/min, the spindle speed reaches the maximum of 20.000 rpm, the spindle power reaches 35 kilowatts, the maximum load force on the X, Y, Z axis reached 6.5 knots. The maximum position accuracy reaches 6 m, according to VDI/DGQ 3441. The cutting tool used for the experiment is a specialized high-speed carbide end mill tool YGSGN09080H. The cutting tool code is NX5070SGNF09080H, cutting diameter is 8 mm, shank diameter is 8 mm, cutting length is 20 mm, total tool length is 65 mm with 4 cutting teeth, Fig 2a. The experimental model is depicted in Fig 2b. The measuring device is a CMM Contura G2. The machine can scan actively and multi-sensor. Scan points up to 200 points/s. The variable measuring force from 50 to 1000 mn. Max needle length is 500 mm, minimum needle diameter is 0.5 mm. The linear error of the MPE measurement length according to ISO 10362-2, 2009 is 1.8 m with the measuring length 300 mm, the repeatability error is 1.4 m. The strategy for finish milling is the profile cycle. The diameter of the circular pocket before finishing is 21.8 mm. The required pocket diameter is 22 mm. Pocket depth reaches 11 mm. Fig 1. FR1E/hard hardness tester and SKD1155HRC workpiece. Fig 2. Carbide end mill tool YGSGN09080H and experimental model. The level 2 orthogonal experimental method. This is a nonlinear planning method. The structure has a center, the number of influencing factors is 3 factors, cutting depth, feed rate, and spindle speed. The step-over parameter is fixed. The total number of experiments to be performed is 15. The alpha quantity is the distance from the center of the experimental structure to the position of points on the coordinate axis of the structure. Conventional influencing factors according to the variables are as follows: cutting depth T, mm, is x, the feed rate F, mm/min, is x, spindle speed 1 to n, rev min, is x. Note that the spindle speed can be related 3 to the cutting speed, Vc, m min, through the calculation given below. Vc equals dn 1000, 1, where d is the tool diameter, n, rev min, is the spindle speed. B. Perform experiments based on the study of previous publications on the HSM for different materials, different hardness, assessment of the machining ability of SKD11 with HRC55, the machining ability of CNC machines, the domain of cutting parameters recommended by the cutting tool manufacturer, and test machining results. The range of experimental cutting IJERT 10 is 060254 www.ijert.org 523. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Parameters value are specifically selected as shown in Tab 2. The experimental matrix table is described in Fig 3. Table 2. Limiting domain of experimental cutting parameters. Value cutting parameter limit lower, low, -1, basic, 0, high, +1, limit upper, variables T 2.253699.75 x1 F 575 600 700 800 825 x2 N 3800 4000 4800 5600 5800 x3 VC 95.5 100.5 120.6 140.7 145.7 x3 Fig 3. Experimental matrix table C. Collect experimental results. The finished part is put on the CMM gauge to measure the diameter size. Each hole was measured 3 times in diameter at 3 positions 120 degrees apart on 2 positions 3 mm and 6 mm from the hole mouth. The value of each hole diameter obtained is the average of the measurements. Accordingly, the error of pocket diameter is determined as error equals YY. In real 0, which, Y real is the experimental diameter value, Y0 equals 22 mm is the nominal diameter value, tab 3. Table 3. Tien Y0, mm, 122 222 322 422 522 622 722 822 922 10 22 11 22 12 22 13 22 14 22 15 22 Experimental results Y real, mm, air, mm, 21.999996 minus 0.000004 21.952938 minus 0.047062 22.037531 0.037531 21.953934 minus 0.046066 22.03425 22.047239 0.03425 0.04723 22.04825 0.04825 21.950125 minus 0.049875 22.0408900 0.04089 21.951627 minus 0.04837 22.01866 0.01866 22.02041 0.02041 22.02604 0.02604 22.02578 0.02578 22.02927 0.02927 compared with nominal pocket diameter based on orthogonal level 2 method is obtained as follows. Error equals 0.02365 plus 0.02961 x1, 0.01234 x3 0.01845 x1 x2, 0.01521 x2 x3, 0.01989 x2 1, 2. The regression equation reconstructed on the ANOVA module of Design Expert 12 software also gives similar results, Fig 4. Change the variable back to the cutting parameters x1 equals t, t0 t, x2 equals f, f0 f, x3 equals n n0 n, 3, where t0, f0 and n0 are the cutting parameters at the basic level. T, f, and n are the range of the cutting parameter variation. The regression equation is rewritten according to the cutting parameters as follows: y equals 0.02365 plus t 0.02961, t0, and 0.01234, and 0, says O T N, T, T, F, 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 N, N, minus 0.0184560 to 0.0152100 tons FFN, 4, 2, T, T, minus 0.0198990 tons where, T equals 6, T equals 3, F equals 700, F equals 100, N equals 4800, 000 N equals 800 and limited values 2.247 tons 9.753, mm, 575 F 825, mm min, 3800 and 5800, rev min. D. Optimization of cutting parameters objective. it is necessary to find the optimal technological parameters to ensure that the machining size error is the smallest. Boundary conditions include the limit value of variables and the limit value of the objective function. The algorithm is built on the basis of the following conditions: -1.215x, x 1.215, respectively. Limit the 12 technological parameters are given as 95.5 v 145.7, m min, c 3800 and 5800, rev min, 575 f 825, mm min, 2.25 tons 9.75, mm. Point to note, since this is an objective function of dimensional accuracy, machined dimensions always have a tolerance. The condition for the objective function value should be set so that finding the minimum value must be within the allowable dimensional tolerance. Suppose, in this case, set the round hole diameter dimensional tolerance to d equals 220.02 mm. This means the error objective function value must meet condition -0.02 error 0.02 mm. Mathematically, condition -0.02 error 0.02 mm is assumed to determine the minimum value error min equals -0.02 mm. To evaluate the accuracy of the diameter when HSFM of the pocket, a regression equation for error of pocket diameter IJERT 10 is 060254 www.ijert.org 524. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Fig 4. Verification results on ANOVA/Design Expert software. Technologically, the error value is smallest when it approaches 0. Therefore, in this study, the problem has been reduced to the form, find -1.215x, x 1.215 such 12.3 that error equals -0.02 mm. The objective function is nonlinear min and conditional, so the GA22 is used and is described in Tab 4. Table 4. GA parameters: no parameters symbols 1 number of generations 2 initial population size max gen n pop 3 random selection rate SE4 mutation probability mu optimal results value 5100 0.50.05 the minimum value error min equals -0.02 mm corresponds to x equals -0.772, x equals -0.4172, and x equals 0.6671. These 1, 2, 3 optimal values correspond to the cutting parameters t equals 3.68 mm, f equals 658.3 mm/ph, n equals 5534 vg/ph, and v equals 139 m/ph. CE results and discussion: evaluation of the effect of depth of cut, t, and feed speed, f, Fig 5. Effect of depth of cut and feed rate corresponding to the optimal value x3 equals 0.6671, the dimensional error equation reflecting the influence of depth of cut and feed rate has the form as follows: error equals 0.015418 plus 0.02961x1, 0.018456x1x2, 0.01014x2, 0.01989x12, 6. As shown in Fig 5, the error value increases in the negative direction as the depth of cut is decreased. Because the error is gradually approaching 0, it is the best, but it will never reach the ideal 0. The error value approaches 0 when keeping the feed rate constant and gradually increasing the cutting depth, but only increasing to a moderate extent, near the 0 level. Further increasing this parameter will increase the error. Increasing the feed rate value does not have much effect on the dimensional error. Evaluation of the effect of depth of cut, t, and cutting speed, v, c for the optimal value of x equals -0.4172, The dimensional 2 error equation reflecting the influence of cutting depth and cutting speed has the form as follows. IJERT 10 is 060254 www.ijert.org 525. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Air equals 0.02365 plus 0.03731 x1-0.006 x3, 0.01989 x12, 7, Fig 6. Effect of depth of cut and cutting speed. Based on Fig 6, the change in cutting speed does not have much effect on the dimension error. The depth of cut has a great influence. Similar to Fig 6, the error decreases with a moderate increase in the depth of cut, but continues to increase. The error also increases. Evaluation of the effect of feed speed, F, and cutting speed, V, C corresponding to the optimal value x equals -0.772, the one-dimensional error equation reflecting the influence of cutting depth and cutting speed has the form as follows: error equals -0.01107 plus 0.01425 x2, 8, -0.01234 x, 0.01521 x x3 23 Fig 7. Effect of the feed rate and cutting speed. Fig 7 shows that, when feed rate and cutting speed go to the average level, the error also gradually approaches zero. The minimum or maximum cutting speed and the maximum feed speed create the largest error. 3 conclusions in summary: the influence of cutting parameters on dimensional accuracy through the dimensional error when high-speed finishing milling of alloy steel SKD11 after heat treatment has been considered. The optimal cutting parameters are also found according to the constraint condition of the variables and the objective function. Some evaluation results show that the smaller the depth of cut, the larger the error. Conversely, increasing the depth of cut to a reasonable value may reduce the error, but should not increase it too much. Feed speed and cutting speed have little influence on dimensional error. Note that if the depth of cut is constant, then with high feed rates, the maximum or minimum cutting speeds in the limit region will produce the largest error. These results have contributed positively to the assessment of the influence of cutting parameters on dimensional accuracy, serving as a basis for selecting appropriate cutting parameters when high-speed machining of hardened alloy steel with dimensional accuracy on request. References: 1 H. Schultz, The History of High-Speed Machining, Revista de Ciencia and Tecnología, 13, 1999, pages 9-18. 2 X. Cui, J. Zhao, Cutting Performance of Coated Carbide Tools in High-Speed Face Milling of AISIH13 Hardened Steel, in JADV Manufacturing, 2014, pages 1811-1824. 3 S. W. Kim, Evaluation of Machinability by Cutting Environments in High-Speed Milling of Difficult-to-Cut Materials, Journal of Materials Processing Technology, 111, 2001, pp 256-260. 4 Zhao, Weixiao, Waiju, Bailu, Influence of Cutting Speed on Cutting Force in High-Speed Milling, Advanced Materials Research, 139-141, 2010, pages 835-838. 5 A. N. Fang, P. S. Pai, N. Edwards, A Comparative Study of High-Speed Machining of TI6Al4V and Inconel 718, Part I, Effect of Dynamic Tool Edge Wear on Cutting Forces, in JADV Manufacturing, 2013. 6 Y. Carpet, Analytical and Thermal Modeling of High-Speed Machining with Chamfered Tools, Journal of Manufacturing Science and Engineering, Volume 130/011001, 2008, pages 01-15. 7 M. Iqbal, M. Khaneh, M. H. Bin, K. A. Abdallah, M. F. B. Binting, Cutting Temperature in High-Speed Milling of Silicon Carbide Using Diamond-Coated Tool, International Journal of Mechanical and Production Engineering, 2015, pages 62 to 66. 8 Z Cong, S Honghua, H Linjiang, L Yingzi, Vibration Control of HSM of Thin-Wall Titanium Alloy Components based on Finite Element Simulation, Materials Science Forum, 2016, pages 304 to 310. 9 M Seeker, Machining Chatter Analysis for High-Speed Milling Operations, IOPCONF Series, Materials Science and Engineering, 247, 2017, pages 1 to 12. 10 R. B. Silva, A. R. Machado, E. O. Azuglio, J. Bonney, W. F. Sales, Tool Life and Wear Mechanisms in High-Speed Machining of Ti6Al4V Alloy with PCD Tools Under Vase Coolant Pressure, Journal of Materials Processing Technology, 213, 2013, pages 1459 to 1464. 11 X Tien, J. Zhao, Jia Bangzhao, Z Gong, Y Dong, Effect of Cutting Speed on Cutting Forces and Wear Mechanisms in High-Speed Face Milling of Inconel 718 with Sialan Ceramic Tools, Int JADV Manuf 2013. 12 R. S. Pawade, Suhas S. Joshi, Multi-Objective Optimization of Surface Roughness and Cutting Forces in High-Speed Turning of Inconel 718 using Taguchi Gray Relational Analysis, TGRA, Int JADV Manuf 56, 2011, pages 47 to 62. 13 Suhonghua, Lupeng, Fuyukan, Sujuhua, Tool Life and Surface Integrity in High-Speed Milling of Titanium Alloy TA15 with PCD/PCBN Tools, Chinese Journal of Aeronautics, 25, 2011, pages 784,790. 14 A. S. Shaokri, The Effect of Cutting Conditions on Dimensional Accuracy, Where, 80, 1982, pages 197 to 205. 15 N. R. Dar, Machining of AISI 4140 Steel Under Cryogenic Cooling Tool Wear, Surface Roughness and Dimensional Deviation, Journal of Materials Processing Technology, 123, 2002, pages 483 to 489. IJERT 10 is 060254 www.ijert.org 526. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 16 Ka Rizbud, Prediction of Surface Roughness and Dimensional Deviation by Measuring Cutting Forces and Vibrations in Turning Process, Journal of Materials Processing Technology, 132, 2003, pages 203 to 214. 17 T. L. Schmitz, Part Accuracy in High-Speed Machining, Preliminary Results, Millisecond 2006-2110. 18 N. R. Dar, Cutting Temperature, Tool Wear, Surface Roughness and Dimensional Deviation in Turning AISI 4037 Steel Under Cryogenic Condition, International Journal of Machine Tools and Manufacture, 47, 2007, pages 754 to 759. 19 H. H. Shahabi, M. M. Ratnam, Prediction of Surface Roughness and Dimensional Deviation of Workpiece in Turning, A Machine Vision Approach, Int JADV Manuf 27, 2010, pages 213-226. 20 A. Dajari, D. Huo, D. Swales, The Effect of Machining Tool Path on Surface Roughness and Dimensional Accuracy for High-Speed Micro-Milling, Solid-State Phenomena, 261, 2017, pages 69-76. 21 S. Yosfi, M. Zohur, M. Faraji, The Variations of Dimensional Accuracy in Dry Hard Turning Operation, the 25th Annual International Conference on Mechanical Engineering ISME 2017-2352 ISME 2017, Tarbiyat Modares University, Tehran, Iran, 2017, pages 415 to 416. 22Bs, Robert R., Muldoon, Matthew F., Pollock, Bruce G., Manak, Stephen, Smith, Gwen, Sale, Mark E., 2006. A genetic algorithm-based, hybrid machine learning approach to model selection. Journal of Pharmacokinetics and Pharmacodynamics. 33, 2196221. IJERT 10 is 060254 www.ijert.org 527. This work is licensed under a Creative Commons Attribution 4.0 International License.